Here's a problem from the British Mathematical Olympiad. A triangle has side lengths of at most 2, 3, and 4, respectively. We want to determine with proof the maximum possible area of this triangle. So, for example, our triangle could look like this, where this side here has side length at most 2, this one at most 3, and this guy here has side length 4. So they're allowed to equal 2, 3, and 4. And the question is, what's the maximum possible area of such a triangle? Let's dive straight into a solution here. Firstly, let's just write out the numbers 2, 3, 4 in a set like this. Now, I argue that at least one of the sides of the triangles has to be one of these numbers here. Hopefully that's pretty clear. If it isn't the case, if I had, say, a triangle like this, where the side lengths are all less than 2, 3, or 4, respectively, well, what I could do is take this triangle and scale it up a small amount. So keep the angles the same, just scale it up a little. And the area will obviously increase, but the side lengths, provided I only increase it a little bit, the side lengths will still be less than or equal to 2, 3, or 4. So therefore, that tells me that one of these side lengths, or at least one of these side lengths, must be from the set 2, 3, or 4 in order for it to have maximum possible area. Okay, so let's just say it's this 4 side. Doesn't really matter. Let's just say that this side here has side length 4. So it's one of the numbers from the set. Well, I actually argue that, in fact, one of the remaining numbers, one of these guys, actually also has to be from the set 2, 3, 4. Why is that? Well, let's draw on this kind of line here. So that line there is going to be the perpendicular height of this triangle. Now, what's the area of this triangle? Well, the area is just a half times base, which in this case is 4, times the height, which is whatever the length of this is here. Now, if both of these sides, 1.9 and 2.8, are both less than the remaining two sides, so here 2 and 3, which they currently are, well, I can make these lines a little bit longer by just extending this baseline and just attaching them to a slightly higher point up here. And this length obviously is slightly longer, but I can still choose it to be slightly longer so that it's less than 2 or less than or equal to 2. So maybe make it like 1.95. And similarly with this guy, make it slightly longer as well, but keeping it less than or equal to 3. But all of a sudden, this new triangle clearly has a bigger area and it still satisfies all the conditions. And so I can keep doing this until one of these side lengths here hits the kind of upper bound of either 2 or 3, whichever one comes first. And so that means if I am to draw a triangle with maximum possible area, it must have at least 2 out of the 3 side lengths from that set there. Okay, amazing. This is actually quite useful because the moment we have two sides of a triangle, we can think of area in a different way using angles. Let's say we have two side lengths of a triangle, let's say A and B, and those are fixed. And we're trying to maximize the area of a triangle which has two side lengths A and B. What we can do is instead of thinking about this third side, we can think about this angle here, theta. And we know that the area of this triangle is a half AB sine theta. So if A and B are fixed, how do we maximize this? Well, the only way we can is by thinking about sine theta to make that as big as possible. Well, the biggest sine theta can be is 1. When does that happen? That happens when theta is 90. And so the area of this triangle is maximized when theta equals 90 degrees. In other words, it's a right angled triangle where the two adjacent side lengths, the 90-degree angle, are the fixed sides A and B. This is really, really cool because now all we need to do is check three possible triangles, three right angled triangles where the two short sides of the triangles are from this set here. Okay, so we could have a right angled triangle where one side's 2, one side's 3. We could have a right angled triangle where one side's 3, one side's 4. Or we could have a right angled triangle where one side's 2 and one side's 4. Now we're just going to use basic Pythagoras' theorem. 2 squared plus 4 squared is going to give us 20, so this would be root 20. This guy here would be root 25, which is 5. And this guy here would be root 13. However, we can actually eliminate both of these possibilities because the hypotenuse in both cases is bigger than, so like this guy here, 5 is bigger than 2, which was what the remaining side length would have to be. Root 20 is bigger than 3. So this is the only possibility that works. Root 13 is less than 4, thankfully. It's less than root 16, clearly. And so this triangle is the one that gives us maximum possible area, satisfying these conditions. What's the area of this triangle? That's easy to compute. Half times 2 times 3 is 3. So the answer to this problem is 3.